Hello everyone, I'm Martin Gubri and I have the pleasure to present you TRAP, Targeted Random Adversarial Prompt Honeypot for black box identification. This is a collaboration between Parameter Lab and Naver AI Lab. In short, we propose a novel task called BBIV to detect the usage of LLM in third-party application, which is critical to assess compliance. And to solve this problem, we propose a novel method called TRAP. And TRAP uses train from suffixes to reliably force a specific LLM to answer in a predefined way. Then, TRAP can be used as a fingerprinting algorithm to identify a specific LLM. We motivate our approach by the fact that private LLM can be leaked. And this happened in the wild. For example, this model on the left was mysteriously uploaded on Hugging Face. And in January, this model was recognized by Mistral to be one of their restrictedly distributed LLM. Tracing the usage of LLM is also interesting for open source models, since they are distributed under restrictive licenses. For example, the Orca model from Microsoft or the Vicuña model from LLMs are distributed under non-commercial licenses. Similarly, Meta forbids deceptive usage of Llama model. And as it was shown by the paper on the bottom right, this type of usage of LLM are real and they power some botnet on social media. The problem of identifying LLM is not trivial to solve, since LLM does not disclose reliably their identity. If we simply ask the model for its identity, something that we call naive identity prompting, we can end up with unreliable answers. For example, here you have some LLMs that don't self-identify correctly. And if they do, we can easily craft some system prompt that can disguise their identity. For example, here we disguise GPT-4 to behave like Claude made by Anthropic. And this works quite well. Therefore, we need specific tools to ensure compliance. We saw two cases, the compliance assessment of open source LLM and the detection of leaked private LLM. In both cases, we have a problem that we called black box identity verification, or BBIV. And BBIV can be summarized as such. Does this third-party application use our reference LLM? Here, we consider a scenario where a LLM provider spends millions of dollars on training a reference proprietary LLM and want to know whether this reference LLM is the same as an unidentified third-party LLM. In our problem, we suppose that we have white box access to the reference LLM, which makes sense in the two cases we saw previously, whether we are an LLM provider that provides a proprietary LLM and we have access to it, or whether this is an open source LLM and we also have access to it. And in this BBIV problem, we suppose that we have black box access to the unidentified LLM, which is deployed by a third-party application, so we don't have access to its weight. And in our case, we will optimize some prompt on the reference LLM using a white box access, and then this prompt will be fed as input to the unidentified LLM. Then we will be able to observe the results of this prompt, and we can conclude whether we obtain some answer that we are expecting, and in that case, the unidentified LLM is the same as the reference LLM, or whether they are different. To solve this problem, we first look at one baseline called perplexity-based identification. In this method, we want to generate text from the reference LLM and from other LLM. Then, we compute the perplexity of this text on the reference LLM. Therefore, we end up with two distributions, the distribution in blue of the perplexity of reference LLM generated text, and in pink, the perplexity of other LLM text computed on the reference LLM. So it's quite logical that the perplexity is lower for the texts that are generated by the same LLM. And the goal here is to set a threshold where we want to separate both. To solve the BBIV problem, we propose TRAP, that stands for Targeted Random Adversarial Prompt. And TRAP is composed first of an instruction, which is a close-ended question. Here, we ask the LLM to output a random string composed of a specific number of digits. Then, to this instruction, we append a suffix, which is composed of 20 tunable tokens. And we optimize these tokens on the reference LLM so that it outputs a specific target answer. Here, it's 314. In general, this target number is sampled at random once at the beginning of the optimization. And when the iteration goes on, we will hopefully have suffixes that force the reference LLM to output the target number. We optimized TRAP suffixes using GCG that was originally proposed for jailbreaking. And GCG is able to force the reference model to output the targeted number that we choose at random. So here on the right, you can see the evolution of the loss of these digits, the target digits, with respect to the number of steps of GCG. So you can see that we are able to decrease significantly the loss of the targeted number. Here, a specification is that we are filtering tokens to avoid explicit leak or explicit copy of the targeted answer in the suffix. On the right, we display the ROC curve to identify the Llama 2 7 billion chat model. And what we can see is that TRAP have a high true positive rate, which means that the suffixes forces the reference LLM to output the target number between 95 and 100% of the time. This is valid for all three LLMs that we looked at. It also have low false positive rate, which means that the suffixes are specific to the reference LLM. They transfer on average less than 1% of the time to another LLM. And finally, TRAP beats the perplexity baseline using less output token. And the perplexity baseline also happens to be quite sensitive to the type of prompt used. So here on the right, you can see that the PubMed prompt, corresponding to the blue line, is best compared to writing or wiki prompt. But this is actually the opposite for other reference LLMs that we looked at in the paper. We also looked at the robustness of TRAP. Since the third party can deploy the reference LLM with changes, we want TRAP to be robust to different types of change. We start on the left with the original model, and we introduce different degree of change to this original model. In blue, we can see that TRAP is very robust to different top p-value. It is also robust to the usual range of temperature, since models are generally not deployed with temperature higher than 1 because it tends to decrease significantly the performance of the model. Unfortunately, TRAP is not robust to some system prompt, since we can find some system prompts that significantly reduce the performance of TRAP. And in orange, we have the percentage of time that TRAP recovers the target answer with another model than the reference model. And here it is equal to 0. This is expected since we want our suffixes to be specific to the reference LLM. In conclusion, we looked at the BBIV problem to assess the compliance of open source LLM and to detect leaked private LLM. To solve this task, we proposed TRAP, which consists into prompt suffixes that are optimized for a reference LLM to output an answer chosen at random. And since other LLM output other answer, we can use TRAP as a fingerprinting algorithm. Future direction might be to have robust identification under different scenarios. The paper, code, and poster can be found in the QR code below. Thank you very much.